So welcome to our next lesson, inductance, as part of the level 3 electrical energy external or electronics external. Today looking at inductors. So basically what an inductor is a electronic component in the circuit that creates charge. Essentially it is basically a wire loop. And ideal inductors have no resistance to current flow, but real inductors, of course, just like a battery, have resistance caused by the wire, which creates an internal resistance. Okay, so in terms of self-inductance, we need to look at Lenz's law. Okay, so from Lenz's law, changing the current changes the magnetic flux. Okay, and this creates or induces a voltage across the inductor, known as a back EMF, which we'll look at soon, which opposes the change in the circuit current. Okay, so when a circuit contains a conductor, depending whether it's switched on or off, it takes time for the current to change, delta I over delta T. And this is due to something called self-inductance, with a symbol of capital L, and depends on two things, the number of coils and the material in the core. Okay, so if you look at the diagrams just there, as a summary, as you turn on a switch containing an inductor, the primary magnetic field will go through the inductor, which will create, due to Lenz's law, a back EMF. Okay, so a current that will oppose that movement. Okay, so therefore the current actually, or the voltage actually decreases, and the current also is retarded in the terms of the circuit being on. And then when you turn the circuit off, now the primary magnetic field and the induced magnetic field are working in unison, okay, through again Lenz's law, because the current now beginning to reduce, and that actually increases the voltage in the circuit, or the EMF in the circuit, kind of interchangeable. So in terms of self-inductance, this is the equation. Okay, basically by changing the current, either by increasing it or decreasing it, you're changing the flux, the magnetic flux in the wire and the circuit itself, and this induces something called a back EMF. And the equation for the back EMF is epsilon B equals negative L delta I over delta T, where L is the inductance in the units of Henri, and of course you're familiar with change in current in amps over change in time, okay, in seconds. And this back EMF is important when looking at circuits, because according to Lenz's laws, this back EMF will oppose the change in current, be it positive or negative. Okay, so when you're turning the circuit on, the change in current will be positive, so therefore the back EMF will be negative to oppose this increase in current. Okay, this also means that the back EMF is limited by the supply EMF, so the maximum back EMF will equal the negative of the supply EMF, but of course due to the fact that you've got this now back EMF working, the change in current over change in time will decrease over time, to the point, using the equation in the previous slide, that the back EMF will basically decrease over time until it becomes zero, and the current will stabilize to the maximum current. Okay, so then when you turn the circuit off, now the back EMF is going to be in the same direction as the supply EMF, to oppose this time the negative delta I over delta T. Okay, because you're going to have a decreasing current. Therefore, the change in current over change in time will not be limited to the supply EMF. This creates a larger magnetic flux, which generates a larger back EMF. So it's possible that you could get some sparking across the open switch. Okay, so in terms of stored energy, when a current flows in an inductor, the energy is stored in the magnetic field, and the amount of energy is dependent on two things, both the size of the current and the self-inductance of the inductor. So the stored energy in an inductor will be half the self-inductance times the current squared. Looking at inducting in RL circuits, analogous to the RC circuits we've used previously, when a battery of an EMF is connected across a resistor and an inductor in series, the current does not rise to a maximum instantly, okay, due to the reasons outlined, and the time is dependent, as we've seen, based on the self-inductance of the inductor and also the resistance in the coil. So the time constant, which again is similar to the one for capacitance, is going to be the time taken for the current through the inductor to increase by 63%, and it's given by the self-inductance divided by the resistance in the circuit. Don't even know about the decay equations there, but you do just have to know the equation so you can make those calculations. Okay, so this is basically a summary of the inductance curves for the circuit. Okay, so basically when the switch is closed, the inductor is in a closed loop with the battery and the resistor, and so the voltages across the circuit must be the sum. That's known as Kirchhoff's law, of course, which we're familiar with. This means the maximum voltage across the inductor going to be basically the same, or the negative of the supply voltage. So the back EMF reduces as the rate of current increases, as you see from the graphs, okay, until the maximum limit is reached. So therefore the current will be basically the supply voltage over the resistance, okay. And when the switch is open, the current again now falls to zero almost instantly. Therefore, the back EMF from the equation of negative L, change in current over change in time, is going to be very large, and this can actually cause sparking. And you see all that from the graphs there. This part is actually transformers. So a transformer is basically two coils known as a primary coil and a secondary coil around an iron core. Okay, so this time, if we use an alternating voltage, so a voltage that changes, and it's applied to the primary coil, this will therefore create an alternating magnetic field, which through electromagnetic induction will create an alternating voltage in the secondary coil. So in terms of transformers, the size of the output voltage, okay, and the current depends on the input voltage across the primary coil and the number of turns in the coil. So from the equation, the primary voltage divided by the secondary voltage will equal the number of turns in the primary coil divided by the number of turns in the secondary coil, which will equal the current of the secondary coil divided by the current in the primary coil. Okay, and the power in the primary coil will equal the power in the secondary coil if it's 100% efficient, which means that if the voltage is high in the primary coil, the current will be low, and vice versa. This is important when we're considering step up and step down transformers later, which is in the next slide, because that means that, for example, if you have a high voltage power line, that means you have low current, and because power loss, W is equal to I squared times R, this means that low current means you get low power loss to, say, heat energy and sound energy if you use those high voltage power lines. And that's probably the reason we essentially do it. Okay, and finally, as I've mentioned also in this slide, efficiency is essentially the power output from the secondary coil divided by the power output from the primary coil times 100%. Okay, so it's not usually 100% efficient due to energy losses. So in terms of step up and step down transformers, so if the secondary voltage is less than the primary, this is known as a step down transformer. So this is a transformer from basically the power pole outside your home to your home. And if the secondary voltage is more than the primary, this is a step up transformer, which means that you've got a higher voltage. Now, this is used to basically in power stations from the, say, 10 kilo electron volts to 200 electron volts or kilovolts associated with the high power lines. And that's pretty much it for transformers and inductance.